today? Everyone's tired. Everyone's ready for the end of the week. Is that safe? Is that safe to say that's the truth or what?
No.
Okay, I'm going to try something a little different. Not different, but something I've done in the past. I just can't seem to want to give up the idea of not putting our lectures online and videos. So I'm going to do this webcam instead. And so I'm going to record the screen. But the problem is I'm limited to staying between this blue and this blue. Unless someone moves it for me, it's just too much of a pain in the ass. So I'm going to just do it this way, okay? Okay. Now, I'll try to get as many examples as I can up there and leave old work up there, but look at this as a compromise. I still get my videos. You still get me on the board. So let's see how it goes. What are we doing today? If you weren't here Monday, all I did was passed out the exams. Anybody need their exams still? Fernando? No? Didn't have any homework, right? So we're ready to jump into 8.6. We're going to do 8.6 and 10.1 today. If we do that, we'll be caught up. We'll make up for that day we missed on Monday. So 8.6, I think you're going to enjoy it. Well, I don't know if enjoy is the word, but I think you're going to appreciate the fact that it's not a whole lot different than things we've done already. So 8.6 is called radical equations. Radical equations. These are like really cool equations, right? Really, really cool.
Easy cool.
They're just radical. All right, so what we've done already are, if we go back to what was on the test, square root equations, right? We did that on the test, square root equations. A square root is a specific type of radical. It's the radical symbol with the 2 out here. That's what a square root is. What we're going to do now with radical equations is kind of broaden our scope a little bit and not have the restriction of having a square root, having the possibility of having cube roots, 4th roots, 5th roots in the equations. And although that sounds terrible, we're really not going to venture too deep into this so the problems aren't going to get too complicated. And the process is exactly the same as the process we had here. Okay? Do it. So here's your first example. Let's say I have the 5th root of 10 plus 5x equals, and we'll go with 3. So we look at it, it's an equation, it has a radical in it, but it's not a square root. It is a 5th root. So we're going to be asking ourselves the question, how do we solve this? It's the same thing. First step was always what with the square root equations? Isolate. Okay, so I'm going to isolate the square root, I'm going to isolate the radical. In this case, it's already isolated, isn't it? That radical's by itself already, by itself on one side of the equation. So I'm good with that step. The second step is to do what? What was it before? Square both sides, right? We're basically raising both sides to the 2nd power so that we get rid of the square root. This time, we can't use squaring both sides because we have a 5th root, so squaring won't have the same effect. What we need to do instead is raise both sides to the 5th power. So I'm going to raise both sides to the 5th power. And just remember that moving on the rest of the day, or the rest of the first half of today, that 5th power is dictated by the root, right? If that was a 6, we would have a 6th power. If it was a 7, we'd have a 7th power. So let's go ahead and do this. I'm going to write the equation down again. Here's my fifth root, 10 plus 5x to the fifth, and then on the right side, 3 raised to the fifth. What should happen on the left side? What should happen? Just the 5 and the fifth root wipe each other out. So all you'll be left with is what's underneath that radical sign. Is that all right? That's the whole idea behind raising it to the fifth power. It's this and this will kill each other off. And if you like things written out as like little properties, basically what we're doing is this. The nth root of something to the nth power is the something. So if I take the fifth root of x to the fifth, it's just the x underneath. That's essentially what's happening here. So on the left side of the equation, what do we have? 10 plus 5x. And on the right side, 15? 3 times 3 times 3 times 3 times 3.
243.
243. Questions? The third step for solving the square root equations is the same as the third step here. We're going to skip that step. But this is the step where you would actually look to say, do I still have any radicals there? If so, repeat the process. We're not going to do that. So that led us on to the fourth step, which was the solving step. And for this equation, 10 plus 5x equals 243. That's a nice linear equation. All we have to do is get x by itself, and we're in business. So let's do it. How are we going to get x by itself? Subtract 10 first, okay? 5x is the only thing left over here, equals 233. And then divide through by 5. And you can get a calculator out or whatever, but I'm going to leave it as a fraction. 233 over 5 is my answer, potentially, because we still have to do the fifth step, which was to check. All right? Check it. So to check it, don't we take this answer and plug it into the original problem? Okay, here I go. I'm going to have the fifth root, 10 plus 5 times what I think x is, which was 233 over 5. And then I have equals 3. And so I want to know if that is correct or not.
So what are you calling number 5, number 4 is solved?
So, check. Sorry, check.
Oh, check, okay.
That's my check step. So what happens here when I plug in this 233 over 5 and then come in and multiply it by 5? What happens to those 5s? They cancel, right? This is like a 5 over 1. 5 over 5 gone. All you're left with is a 233. So 10 plus 233 is 243. So here's where I'm at. I have the fifth root of 243 equals 3. Is that true or not? Yeah, right? Fifth root of 243 means, or if I'm going to say fifth root of 243 equals 3, that means if I take 3 times 3 times 3 times 3 times 3 5 times, I should get 243, which you can check for yourself is true. So it checks. All right? How about this? Fourth root 2 minus 3x minus 3, or let's say, yeah, we'll go minus. Minus 3 equals 0. First step, do you want to see if you can do this one?
Yeah.
You want to try it? Okay, see if you can get it. If you get an answer, let me know. It's the same process. If you want, you can look up here to see the steps and ask me any questions. Raise your hand if you aren't getting a certain part of this. Following here, any questions? Take your time. You zone down. You all right? Just are you checking? It's free care. Okay, yeah, yeah. Just give maybe one more minute. Questions? Do you have a question? You're looking
No,
like
I'm
you
just
did.
gonna see if you did the same thing that I did the same thing that you did.
Divide by, did you multiply both sides by -1/3? Is that what you did?
Oh, no, that's why it's too bad, okay. I just started solving before the.
All right, I'm going to walk through the steps real quick. The first step was to isolate the radical, so added 3 to both sides to get this. Then raising both sides to the 4th power will eliminate the root on the left side. 3 to the 4th power, 3 times 3 times 3, 4 times is 81. Skip the 3rd step. Take this equation here, solve it for x. So subtract 2 on both sides to get 79. Divide both sides by -3. So over here you get just the x. 79 divided by -3, that's why I have the negative out front, because it was a positive divided by a negative. Then I take that answer and I plug it back into the original problem to check it. So I'm going to plug it in for the x. So that's right here, 2 minus 3 times -79/3. The 3's will cancel, and a negative becomes a plus. So that's why you have a plus 79 here. And then 79 plus 2 is 81. 4th root of 81 is 3. So everything checks out. Yes?
Is there any instance where you would not leave that as a fraction? If it was something like 25/5.
Sure. Okay, yes. If it was a nice integer, you would, or if it reduced, like let's say you got 4/8, you could get like 1/2. But yeah, anytime it would reduce, go ahead and reduce it. Okay, this all right? This straightforward. Like I said, it's very similar to what we've done already, isn't it? Except for that step with the squaring, or squaring could be anything now. Cubing, fifth power, 6th power. Now, give you one more type, then we're going to move on. The next type is something like this. Let's say we have the 7th root of 100x plus 1 minus the 7th root of 2x minus 1. Well, let's make it minus 10 equals 0. If you go back in your notes, when we did square root equations, we started out with very basic ones, and then they started to get more complicated. And there was even one that I told you, I promise you this is going to be on the test. And it was. It was the one where you move things over, you had to square and you had to FOIL out. Okay, these problems, kind of the same way. They could build up and get more complicated, but we aren't going to. We're going to keep them very simple. This is really the only other type that we're going to have to look at right here. The main idea today is that if you ever have an equation with a root that's other than a square root, you can do this. Raise both sides to whatever power. That's the main thing you have to walk away with today. So steps. First, isolate the root, right? Now we have 2 roots. So same story. We isolate, we pick one, we take the other one to the other side. So I'm going to choose to take this one and leave it here, which means move this one to the other side, which means add it to both sides, right? When I add that root, it just really appears on the right side now positive, doesn't it? Okay, so I'm going to write this as step 1. Isolating. I'm not going to show that work. I'm just going to show what we get.
Does it make a difference which one you move?
It won't make a difference in terms of the answer, our final answer. What it does make a difference with is how you might get confused with signs. Like if I took this root to the other side, this one would still be negative over here, and the one that moved over would go from a positive to negative. So you have negatives on both sides. And so when you raise that to a 7th power, which is what we're going to do, you'll still have negatives. So the signs might start to mix you up. I guess, rule of thumb would be try and make it where they're both the same, they're both positive. So that's our isolation. Now what? Raise it to the 7th on both sides. Raise to 7th power. raised to the 7th power. Good things are about to happen. We're going to take the 7th root of 100x plus 1 and raise it to the 7. And on the other side, the 7th root of 2x minus 10 and raise it to the 7th power. Do you see what good things happen? See it? Look, the 7 and the 7th power cancels on both sides. And so the roots are basically gone, aren't they? And what are you left with? 100x plus 1 equals 2x minus 10. Nice equation again. And then I go through and I, skip the 3rd step, right? And then on the 4th step, I solve this. I'm intentionally giving you problems where your answers are not nice numbers. They keep on turning into these weird fractions. So for isolation of x here, I'm going to just subtract 2x on both sides to give me 98x. And I'm going to take the 1 to the other side, which gives me negative 11. And finally, do what? Divide by 98. That is our potential answer. We have to still plug it in, don't we? Questions on this step? 2x, subtract on both sides, 98. Take the 1 off this side, subtract 1, subtract 1. Divide through by 98. Shall we check? This is going to be a weird check, all right, as you're about to see. And try and plug that into here. Oh, wow, okay. I have 7th root of 100 times my potential answer is negative 11 over 98 plus 1 minus, okay, 7th root of 2 times negative 11 over 98 minus 10. Does that equal 0? Is that not weird or what? Yes. That is strange. So how, things aren't going like they're not real clean here, right? Things aren't going away like they did in the previous problems. So let's try and figure out what this is. 100 is 100 over 1. I'm going to multiply straight across. 100 times negative 11 gives me negative 1100 over 98 plus 1 minus 7th root over here. The same thing with the 2. The 2 is like a 2 over 1. 2 straight across gives you negative 22 over 98 minus 10. Does that equal 0? Well, that's still not a very nice looking thing, is it? Right? That doesn't look very nice. But can't we get a common denominator here? Can't we get a common denominator right there? So I would turn the 1 into a what? 98 over 98. Remember, 1 is like 1 over 1. So you multiply top and bottom by 98. So this becomes 7th root negative 1,000 over 98 plus 98 over 98. You have to do the same thing on the other one. What?
100 times.
Oh yeah, I forgot something. What am I missing here? It should be a 1. Thank you. I'm glad you caught that. This one over here, still negative 22. Here's my 7th root. Negative 22 over 98 minus. Now I need to turn my 10 so that it has a 98 on the top and bottom. I mean, sorry, on the bottom. So multiply the bottom by 98 and the top. 10 is like 10 over 1. So won't that be 980 over 98? Do y'all see what I'm saying or not? This right here, same denominator I need, so I multiply top and bottom by 98. 98 on bottom, 980 on top. Does that equal 0? The numbers are ugly here, right? If we have the same denominators and I want to add, don't I just take this and add it to this? Negative 1100 plus 98. What's negative 1100 plus 98? Negative 1002. Good. So we have the first one, 7th root, negative 1002 over 98. Then the other one's minus 7th root of, now here, don't we have the same denominator? So I take the negative 22 and I subtract 980. What's negative 22? Take away 980 more. Negative 1002 over 98. Does that equal 0? These are exactly the same, aren't they? I have the 7th root of negative 1002 over 98 minus the 7th root of negative 1002 over 98. They're exactly the same. Something minus itself is 0. Check. So the checking part of this one was the hardest part, right? So what I wanted you to see here is just how, you still might have to mess with some fractions in here. It's a healthy exercise. All right, that's pretty much it as far as the section 8.6 is concerned, right? As far as 8.6 is concerned, we're not going to get into anything else. The homework, does someone have their book? Can I see the book? So I can give you the homework assignment out of that section? I just want to confirm the problems that I have in my head are correct. Thank you very much. So 8.6. The homework here is page 570. And you can look at 21 through 31 odd. Okay. All right. Now, let me start our new chapter, new section. This is going to be chapter 10, section 1. We're going to start looking at complex numbers. Complex numbers. 1 o'clock. Got a ways to go here. You all right? Complex numbers. All right, so let me try and make this a little more interesting for you by starting off with something that might grab your attention. Has anyone here ever heard of this before? Or seen that before? Other than, yes, that's a vowel, I. In mathematics, have you seen this before? Imaginary numbers, have y'all ever seen I for imaginary numbers? I is what we call the imaginary unit. It's very similar to an important number that you learned when you were very, very young. And that would be the number 1. Okay, the number 1 is what we would call the real unit. In the real numbers, right, the number 1 is one of the first numbers that you ever learn, isn't it? And so once you've got one down, you can kind of get through the rest. And if you, people who believe in kind of like the evolution of the human thinking, believe that 1 was the first number we ever could make sense out of. And that the next number after 1 was 2. You know, it's like I'm walking around and I'm, you know, got some rocks or something, and, you know, the idea of 1 and then 2, and, you know, that was all, those were the first things, those numbers, 1, 2, 3, 4, 5. And then the big, like, discovery, back when our brains were very primitive, was the idea of 0. The idea of nothing was it was a huge leap, I should say, for us to actually understand the idea of nothing. And so 0 came later, and then -1, -2, and then the fractions came into play, and all this other stuff. And what we do is we get the entire real number line, right? All the numbers you've studied your whole life. Everything, you've always had solutions. X equals 2, X equals -5, and everything has always been a real number. 1 is called the real unit. It's the number with length 1. Okay, unit means 1. Okay. So the imaginary unit is almost like that first, very basic first step for understanding what are called the complex numbers. So all these together, right? All these together called the real numbers. And then once we start talking about the I, start getting the I involved, you create a big system of numbers here called the complex numbers. Now here's the problem. When I was first conceived, when the idea of I was conceived, a lot of mathematicians math people did not believe that it made sense. And so it got, unfortunately, the stigma of being imaginary, of being kind of made up. And so for many, hundreds of years, the people who were studying I were kind of looked down upon by other mathematicians and scientists, because they're just like, I don't know what these guys are smoking, but they're wasting their time here. That's basically what it was. That's what it seemed to be. And the reason why is because I, by definition, it's called imaginary unit, but I, by its definition, is actually what the square root of -1 is. That's I. I is the square root of -1. And we've always said up to this point that whenever you try and take the square root of a negative number, we can't do it, right? We'd say no real solution, no real number. This is a non-real number. And that's true. This is a non-real number. Because there's no real number, there's no number you can grab off the number line, square it, and get a -1. There's nothing we can grab off the number line that'll work. But there is a number that you can grab outside of the number line in the complex numbers called the imaginary unit, I, and it is by definition the number that when you square it you get -1. And so, do you see why this is kind of seems like made up almost? It's like I'm sitting here and I'm just going to say, I'm going to call this thing, which has no real definition, like we can't figure it out in our number system. I'm just going to call it I. That's like me calling the pink elephant in the corner of the room that has no wings, my friend over there, calling her Daisy. Is that okay? I mean, I can call it anything I want, but if it doesn't exist, it doesn't exist. Who cares, right? That was the big debate. That was the big dilemma. By the way, on a side note, the pink elephant in the room over there with no wings. This is a logic problem for you. If I say to you that every pink elephant in this room has wings, is that a true statement or a false statement? All the pink elephants in this room have wings. No, just that statement. The statement I just made, is it true or false? That all of the pink elephants in this room have wings.
Oh, you just said not one did.
That's a different one. That's a different shade of pink. No, I mean, think about the question. I mean, it's either true or false that all the pink elephants in this room have wings.
True.
It's true. Now, here's why it's true. Because of the way logic works, you can't prove it wrong. Okay? In order for you to prove that wrong, you must produce a pink elephant in this room that does not have wings. And you won't be able to do that. So this is something that we call being vacuously true. Anything based on a false premise is true. Right? If I say, the blue marker in my hand, is also a laser beam. Well, that's true because I don't have a blue marker in my hand. It's weird. If your assumption is false, your conclusion is always true, and that's the way our logic works. Now, I went off on a tangent there because that's not really related too much to this, other than the idea of, look, this seems so crazy that someone sitting here trying to define what this is, all the other math people are like, look, we don't have numbers that do that. Why do you keep trying to do it? Well, we'll just call it I. Okay, weirdos, get out of here. Whatever, That's the way it was for hundreds of years. Until a mathematician came around and was able to prove that this has to exist. And it's beyond the scope of this class, but it has to do with, I don't know if you've ever solved the quadratic equation. Y'all have learned the quadratic formula before? Negative b plus or minus square root b squared minus 4ac all over 2a. That big equation they give you to solve quadratics. Seen that? Heard that? Well, it's tied into that. Turns out that there's another equation for cubic equations. And in that equation, you wind up getting a square root of a negative. And the solution must exist, which means this must have meaning. And so later on, hundreds of years after this was already called the imaginary, the guy came out and proved it, and everyone's like, oh, okay, that has to be real. So, I mean, not real numbers. It has to be significant. It has value. And then a whole branch of mathematics grew out of this. Okay? So we're going to study I today. I want to give you one more analogy. I gave this to my other class. It might help. Because no matter what I say, if I call something imaginary, you're not going to believe it's true, right? Right? I'm going to be calling it the imaginary numbers. Imaginary numbers. It's all fake. So let me help guide you in the whole process of maybe putting some value to the I. I call this the fishbowl theory or concept. Here's a fishbowl, and you have in here fish. They're my fish in my fishbowl. And they're happy in there, right? As far as they know, every so often, someone comes and drops food in there, right? And they live, whatever. Do you think that they have any concept or any idea of what a truck is? No, probably not, right? Or in terms of animals, do you think that a goldfish or whatever that is has any idea of what a mountain goat is? And let's not even think about the fishbowl anymore. Let's think about like animals in the ocean. Do you think that a whale knows what a shark is?
Yeah.
Probably, right? I mean, there's a natural, there's an ecology in that ocean that has, you're afraid of this, you want to eat that, right? Everyone knows their place. But the ocean animals probably don't really have any idea what a mountain goat is or what a camel is, right? Does that mean that the camel doesn't exist? No. That's because these fish are stuck in their bowl. And us, as we are raised as children in this world and we are given an education, we are taught about the real numbers. Okay? We are taught there are real numbers. And this is what we use to do all of our math. There they are. And that's your fishbowl. That's where you live. Turns out, though, that there are mountain goats and there are camels and there's the imaginary numbers that actually live outside of this. Okay, this imaginary number, is outside this fishbowl. Just like over here, the camel's outside the fishbowl. Am I making any sense at all here? Okay, the camel's real, the I is real. And you have to be able, in mathematics, and unfortunately, we're not going to be able to really get into the I and the complex numbers because they're very complicated. They require you to be able to visualize things in 4 dimensions. I mean, we live in 3-dimensional space, right? 3D is like, okay, there's depth, there's width, there's height. That's 3-dimensional space. To actually understand complex numbers, you have to visualize 4-dimensional space. Much more difficult to do. So a lot of times, complex numbers and how they work into mathematics and how they all blend together isn't studied till after calculus. After calculus. Which is why I've always had kind of a problem with books wanting to introduce the imaginary number now. To me, it's too early. It's just like, look, oh, nope, you don't get to see anymore. That's it, bye. And that's all you get, okay? But even doing that, it even just kind of makes you more confused about it because you're like, okay, for just like a couple of days, we talked about the square root of -1, and I never saw it again. Never, ever saw it again. And so it just kind of solidifies the feeling that that thing doesn't make any sense. So, y'all understand my fishbowl theory? I'm going to give you one last thing that's going to hopefully drill in at the end that this is something valuable. It goes back to art. How many of you like art? You hate math, you like art. You like art, you like maybe art history, drawing. Anyone like drawing? Any drawing people here? Okay, you like to draw? So if I asked, well, if I asked a caveman to draw me something like, maybe I shouldn't say caveman. Caveman wouldn't know how to draw this. Let me say I'm drawing a road, right? And let's say this is some like buildings on the side of the road. This is like my classic example of this. Is that a road, looking from the top, is that a road with some buildings on the side?
Yes.
It's a pretty good drawing, isn't it? Okay, now, when I'm drawing this, I'm following some very basic rules. On a road, when I draw my road, the curves of my road shouldn't hit each other, right? And these buildings, the walls should be parallel, right? Notice that in my picture, all of my parallel lines are all perfect, aren't they? Great, parallel lines. Y'all see that? And that's because I'm trying to use the rule that parallel lines shouldn't hit each other, right? If I drew a road like this, I said, here's my road, my buildings are like this, and here's a building, and I said, okay, that's my top view. You'd just be like, what the hell's up with that road? You know, it's all messed up. You know what I'm saying? They look all weird. So I'm following some fundamental rules when I draw that. Namely, parallel lines don't hit each other. And for a long time, if you look back in the history of even art and drawing, this fishbowl of parallel lines can't hit kept drawings pretty bad for a long, long time. And then mathematics caught up, and we were able to determine, look, if you're going to try and draw something the way your eye is seeing it, then you're going to have to do something to trick your eye. And the first thing you're going to have to do is break all the rules in your fishbowl. The first one being that parallel lines can't hit. I need parallel lines to hit in order to make it look right. So here's the same drawing using mathematics. Now my new rule is that all parallel lines will hit each other at a single point. So there's my road now. My 2 curves of my road are going and hitting at a point. Here's the edge of this building down here. That's this edge. That's also parallel to the road, so it should also go towards that point. And then I'm just, you know, here's the other edge of that building over there. Okay, that's the right side, that's here. That should also point towards that point. And now I'm just going to start filling in all the blanks, and I'm going to do it real fast. Okay. Actually, I don't like that. Okay, there's a building now. See it? Okay, all parallel lines are headed towards that point, which we call in mathematics or in art and stuff like that, they call it the vanishing point. And then we make the horizon. So there's your horizon. And now you have a good drawing, right? I'm not good. I'm not claiming that's good, but sure is better than this, right? I mean, that looks more realistic than this does. But I had to break a fundamental rule. Parallel lines don't hit. Here, parallel lines do hit. This over here is called Euclidean geometry. This over here is called perspective geometry. So you have totally different geometries. Fishbowl, bigger, different fishbowl, okay? So I hope that kind of helps you understand that, look, even though we're only going to take a small dive into imaginary numbers today, that there is a value in it. So if anyone ever gets on that show, Who Wants to Be a Millionaire, or a quiz show, and the final question is true or false, all parallel, parallel lines don't intersect, false. And then I get half the winning. All right, let's get back to this. We are going to define I as the square root of -1. That's the definition. I is that thing that when you square it, you get -1. In other words, I squared is -1. And this is the big one we need to know. I is that number that when you square it, you get -1. Now, there's a couple of other things we can do here. I cubed, what would I cubed be? Let's see, let me try it this way. How about I cubed, isn't I cubed I squared times I? Isn't that the same thing? I cubed is I times I times I. So I have two of the i's. Here's I squared and here's I. What was I squared though? -1. So isn't this -1 times I? And isn't that just -I? A negative in front of a -1 in front of something is the same as just that negative. Y'all see what I'm saying or not? You got it? So I is just I. That's the definition. I squared is -1. I cubed is -I. Let's do one more. What's I to the 4th? Try it this way. Isn't that I squared times I squared? Isn't I to the 4th I squared I squared? What's I squared? -1. Isn't that -1 times -1? What's -1 times -1? +1. This little demonstration here shows something about imaginary numbers that's kind of weird. Imaginary numbers, when you put them together, like when I multiplied two imaginary numbers together here, right? When I took I and I multiplied it times itself, I actually got a number that we all know, -1. So I took the imaginary unit, I squared it, and I actually got a real number. And then I took the imaginary number and I cubed it, and I got an imaginary number. But if I raised it to the 4th, I actually get a real number. So we have this, I mean, they are very much connected to each other. All right? It's kind of odd. Y'all see how I got it though? Okay. So what are you going to need to be able to do in here, right? At the end of the day, that's really what you kind of want to know. What am I going to need to be able to do? Well, we're going to need to be able to add and subtract imaginary numbers. So let's look at this. Find what 2 plus 3i minus 4 minus 2i is. Now we don't want to overthink this. Again, I just opened the window and closed it. We don't get to ask a whole lot of questions about the imaginary numbers, but we get to operate with them, just basic algebra. So I would like to get rid of parentheses and put this all together. So the only thing I have to worry about is that minus sign needs to be distributed through. I don't have to worry about this parenthesis out here because there's really a 1 in front. So my next line can be 2 plus 3i minus 4 plus 2i. And then let's combine like terms. So just as you might imagine, things without i's go together, things with i's go together. So my 2 take away 4 gives me -2, and then 3 i's plus 2 i's is 5 i's. There we go. That's it. That's your answer. So this would be considered adding and subtracting imaginary numbers. So what do you think comes after adding and subtracting? Multiplying, right? And then dividing. So next thing I'm going to do is ask you to find, let's multiply 2 imaginary numbers. Let's find what 7i is times -3i. Okay, so the 7 and the -3 will multiply to give us -21. And then you have the I and the I, right? Multiply also. I and I together multiplied is I squared, isn't it? But I squared is -1, isn't it? That was the one I said you all needed to make sure you remembered. I squared is -1. So now what happens is we get -21 times -1, right? Which is 21. So on your 21st birthday, when you become you can legally drink, is really your 7i times -3i birthday, right? 7i times -3i is really just a fancy way, or just a crazy way of saying the number 21. That's all it is. But the only way we got that is because this I squared became -1. So somehow putting the i's together like this turns it from imaginary back into a real number. Weird. All right, let's do another multiplication, this time something that requires some distribution. How about -4i, 2 minus 3i? This one required just pure multiplication, nothing, we had no plus or minuses in here. This one, though, has a subtraction in here. So we look in the parentheses, can you put 2 minus 3i together? No. So we're just going to distribute now. See if you can distribute that, see what you get. And just remember that when you do that, I squared turns into -1. If you get it, raise your hand. I want to come see what you have. What's I squared? What is I squared? -1. So you turn into -1. This is I squared. So you can't put it together with the -8 on. The -8 will be on the front. There's an I on that -8. And then on the last one, it's 12 times I squared, so 12 times -1. That'll be multiplication, yes. Yep. And you won't be able to put those together. The -8 on, we'll leave it out in front of whatever that is. Okay. -8 on. Be careful, it's multiplication. 12 times -1. That's the most common mistake. Same thing. 12 times -1, not 12 minus 1. Okay. -8i here. -4 and -3 is positive 12. I times I is I squared. So I squared back there. What did you get? Okay, that makes sense? You good here? This time is just the -4 times the 2. I think you're making it harder than it is. You could do it that way, but it doesn't matter. Yeah. There is a standard way to write it. You're normally supposed to put the I stuff in the back, but it's not wrong that way. You get it? I mean, does that make sense? Hmm? I'm just trying to figure out if that's the right answer, but this right here becomes negative because I squared becomes -1. Change that to everything else is negative 8 on minus 12. You can get plus minus. You get it over? Got your negative 8 on. You can just this. I don't need this here. So you do negative 4. And then that was in front of it. So you have negative 8 on, minus 12. Because they're side by side. Okay, I think we've got it. Negative 8i minus 12. How about this? See if you can get this one. 4 plus, I'll make it minus, just because I know you like the signs to be messed up, so I'm going to make it minus for you. 4 minus 5i squared. What does that mean? Be careful. Don't make the mistake. I don't want you to get too far. This is a FOIL problem. You should have that. Make sure you've got that times itself, and then FOIL. That's what you should get. It can be negative 40i minus 9. That's fine. Yep, you can have it either way. You okay? Questions at all? No one has questions? Sure? This one seemed easier? Okay. All right, that's pretty much going to cover what I'm going to ask you to do for homework as far as, we're going to do division next time because we need a little more time than we have today. I'm going to borrow this.
Sure.
For the homework, for homework, please do page 639. Numbers 9, 10, 11, 21, 23, 33, 37, 41, and 45. But I just realized, don't pack up, I just realized I forgot to show you something. I think you'll pick up real quick on it, so don't worry. It's not going to be like way complicated. I started multiplying, adding and multiplying right away, but I forgot to show you this. If we say that the square root of -1 is I, right? Then if someone comes and asks you now, what's the square root of -4? We can actually answer this if we're allowed to use I by doing the following. We can first split this up into 2 radicals, rewriting -4 as 4 times what? -1, right? Now what's the square root of 4? 2. And what's the square root of -1? I. So the answer is 2i. Right? If I asked you what's the square root of 4, you'd say 2, right? But as soon as I put a negative in there, it becomes an I. Here's another one. I'll put it above. What's the square root of -45? Well, as soon as you see the negative there, you know you're going to have an I, right? But let me write it out. This is the same as square root of 45 times the square root of -1. My square root of -1 is going to turn into the I, right? But now you have to break down square root of 45, just like you've been doing all semester long. You try and break 45 into be 2 numbers, however you're comfortable doing it. It would turn out to be 3 root 5. So you should get 3 root 5. And then the square root of -1 is what? I. Now we don't normally write it that way. We always like to put the I over here in front of the root. So we write 3i root 5. That would be it. That make sense? There's kind of a rule of thumb if you want. If that negative wasn't there, our answer would have just been what? 3 root 5, right? But as soon as there's a negative underneath the root now, a square root, we know that we can just get rid of the negative and just throw an I on the outside. Right? Square root of -121. Well, I know I'm going to have an I. And then what's the square root of 121? 11. So times 11, I don't write it that way, I write 11i. Make sense? All right, I do want to take attendance. We have quite a few people not here today, so I don't want to encourage that by not taking attendance. So I'm going to take attendance, but let me stop the video